Yo, what's up? Ricky Sanders here. If you live for fast cars, greasy hands, and solving problems under the hood, welcome to your new favourite spot. I'm all about real fixes, no BS, and showing you how to keep your ride running like a champ. So go ahead, smash that like button, hit subscribe, and let's make some noise in the garage. Enough talk, let's get wrenching.
The main difference between the inlet valve and the exhaust valve is the diameter of the plate. The inlet valve has a larger diameter. Why? Because the suction of air from the atmosphere into the cylinder under the action of rarefaction occurs at a slower rate than its ejection from the cylinder by the piston. It's simple, the amount of air, or fuel-air mixture, is the same, but the speed is different. Accordingly, where the velocity is lower, the bore is wider and the plate covering it is larger in diameter. All this is true for those valve arrangements where there are an equal number of intake and exhaust valves, 1 or 2 each. However, there are motors with an odd number of valves, 2 intake valves plus 1 exhaust valve or 3 intake valves plus 2 exhaust valves. The opposite is true. The diameter of the exhaust valve plates will be larger than the intake valves, because the manufacturer compensated for low intake velocity by adding 1 extra hole, not by increasing the diameter. You can read more about valve-to-cylinder ratios in the corresponding article. The second important difference in valve design is their operating temperature. Inlet valves work at 350 to 500 degrees, but the exhaust valves are heavier. Red-hot exhaust gases heat them up to 700 to 900 degrees. Therefore, exhaust valves are often made more heat-resistant. The inlet and exhaust valve heads, or plates, can be of the same diameter or different diameters. On older brands of cars with small valve overlap, my note. Usually the intake valve head is made larger in diameter to improve cylinder filling. For example, the size of the valves of the GAZ 53A car engine, the diameter of the inlet valve head is 47 mm, and the exhaust valve head is 36 mm. In the CAMAZ 740 diesel engine, the diameter of the inlet valve plate is 51 mm, and the exhaust valve is 46 mm. The inlet is large, the exhaust is small. Engine exhaust valve. The exhaust valve is a component of the timing system which, when opened, removes, exhausts, exhaust gases from the engine combustion chamber. Exhaust occurs when the piston in the engine cylinder moves from bottom dead center, BDC, to top dead center, TDC. During engine operation, the exhaust valves are subjected to significant thermal stresses because they are constantly in contact with hot exhaust gases. The valve head can heat up between 600 to 800 degrees Celsius when the engine is running. After the end of the intake and compression stroke, the main requirement at the time of ignition of fuel in the combustion chamber is maximum tightness. The inlet and exhaust valves are closed. When the piston has absorbed the energy of the expanding gases from the combustion of the fuel-air mixture, these exhaust gases must be removed from the combustion chamber. Sealing the chamber is no longer necessary at this stage. The exhaust gas removal in the timing design is the responsibility of the exhaust disc valve, which is located in the cylinder head, cylinder block head. At the intake stroke a rarefaction is created, and at the exhaust stroke an increased pressure is created in the combustion chamber of the engine. After combustion of the fuel-air mixture, the exhaust gases leave the combustion chamber through the exhaust valve, which opens at the right moment. The pressure force allows the gases to escape from the combustion chamber with ease. This explains the smaller size of the exhaust valve disc compared to the intake valve disc. At the intake stroke, the rarefaction is less in strength than the exhaust pressure. The exhaust gases are practically pushed outward through the open exhaust valve. Effective sealing of the combustion chamber is made possible by the use of disc valves in the timing design of modern internal combustion engines. The valve device is simple. The element has a plate and a rod. The chamfer smoothly transitions into the stem, which makes the valve strong enough. The conical shape of the transition noticeably reduces the resistance of exhaust gases when leaving the chamber, and also further improves sealing. The exhaust valve is opened by the force generated by the camshaft can. The valve stem is located in the valve guide sleeve, which is pressed into the cylinder head. The camshaft cam presses directly on the valve stem or rockers, from which the force is transmitted to the stem. The cylinder head also houses the valve seat. The valve seat is a recess that is shaped to match the top of the valve plate. The valve plate and valve seat are pressed together with filigree precision. This solution ensures maximum tightness when the inlet and outlet valves are closed. The main objective is to prevent gases from escaping from the combustion chamber. There is a special notch in the upper part of the valve stem. This notch is the location of the dryer. This dryer is a conical ring, which is cut into 2 equal parts. The solution is necessary for fixing the valve spring plate. If the opening of the valve is realized by the push from the camshaft can, then the closing of the valve is realized by the force of the valve spring. Said spring closes the valve by pressing the plate firmly against the seat. In addition, there is a mechanism that rotates the valve. This is necessary for even wear of the valve and for cleaning the valve of soot. The exhaust valve works under extremely difficult conditions. Exhaust gases cause severe corrosion of the exhaust valves. If the fuel does not burn completely in the chamber, then this can lead to valve burnout. Valve adjustment is an important procedure in the operation of an internal combustion engine. Early closing of the exhaust valve can lead to rapid valve burnout. During the operation of any internal combustion engine, the valve plate and seat become covered with soot. It is practically impossible to avoid soot on the valves. The presence of soot causes constant overheating of the exhaust valve. Sooner or later the valve bearing surface starts to burn out, which leads to loss of tightness in the combustion chamber. The result is progressive loss of engine power, difficult starting, etc. The microcracks in the valve plate caused by overheating gradually enlarge as the pressurized hot gases start to burst out of the combustion chamber. The valve head deforms under these conditions and further deteriorates. Failure of the valve actually means a complete loss of functionality of the engine cylinder. After replacement, it is mandatory to lapping the valve to the seat for the most accurate fit. Ignoring the procedure or performing valve lapping poorly will result in rapid failure of the new valve. It is quite obvious that overheating is a serious problem with exhaust valves. A special chromium nickel molybdenum steel is used to make the exhaust valve. The base is nickel, which increases the resistance of the exhaust valve to mechanical failure. The valve steel is characterized by high heat resistance. The next step to reduce the thermal load of the exhaust valve is its design, which is different from the device of inlet valves. The exhaust valve stem is hollow and the cavity is filled with metallic sodium. The sodium melts and flows inside the valve stem to improve heat transfer and evenly distribute heat. The exhaust valve can also have additional protection, which can significantly extend the service life of the element. The only disadvantage can be considered the final cost of production of the part. Among the most common methods of protection are laser alloying, plasma powder cladding method, high-frequency current cladding, plasma. Powder cladding is considered to be one of the most economically and practically justified solutions. Various metal powders based on cobalt or nickel are used for this type of surfacing. The coating technologies are different, but the main task of each of these methods is to clad a thin layer of protection on the surface of the valve to increase wear resistance to corrosion and mechanical destruction. Engine intake valve. The intake valve is an element of the gas distribution mechanism of an internal combustion engine, which is responsible for the passage into the working combustion chamber of the fuel-air mixture, or only air, for diesel engines or direct injection motors. The intake timing valve opens access to the engine cylinder and then closes access before the compression stroke begins. Inlet valves are made of special steel. There are specific requirements for such steel for the manufacture of internal combustion engine valves: high surface hardness, sufficient thermal conductivity of the material, narrow coefficient of thermal expansion, resistance to the corrosive effect of combustion products. The ability to withstand regular dynamic loads at high temperatures. Additional requirements for valve steel imply that there is no hardening effect when the valve cools down after operation at high temperatures. This means that the steel must not become brittle on cooling down. None of the steel grades developed today meet these requirements 100%. Internal combustion engine valves are made of high-alloyed silchromes, which allows this part to work under the highest heat conditions. This approach has ensured the necessary strength of the valve, as well as the ability of the element to resist corrosion processes, which actively progress in the environment of its operation at high temperatures of about 600 to 800 degrees Celsius. The valves are placed at a certain angle, 30 to 45 degrees, with respect to the vertical axis. The difference between the inlet valve and the exhaust valve is that its plate has a larger diameter compared to the plate of the exhaust valve. This difference is due to the fact that the opening moment of the inlet valve occurs precisely at the time when the combustion chamber becomes rarefied. At the moment of release, there is an increase in pressure in the cylinder. The vacuum in the cylinder at the inlet is inferior to the pressure at the exhaust stroke. For the best and most complete filling of the working fuel-air mixture at the inlet, valves with a higher flow capacity are required. This capacity is realized by increasing the diameter of the inlet valve plate or the number of inlet valves. The intake valve disc is flat on the combustion chamber side, but on the camshaft side it has a cone shape. This cone is also called a chamfer. When the intake valve is closed, the chamfer is pressed against the valve seat, which is also a tapered hole in the cylinder head. Precise fit of the inlet valve is ensured by the use of a guide sleeve. The valve stem is inserted into the sleeve and the sleeve itself is called a valve guide. The valve guides are pressed into the cylinder head housing and additionally secured with a retaining ring. Modern powertrains tend to increase the number of intake valves per cylinder to improve flow capacity, increase the efficiency of filling the cylinder with a working fuel-air mixture and improve power and other characteristics of the internal combustion engine. The valve receives an inner and outer spring. These cylindrical springs are fixed on the valve stem. The opening of the intake valve at the intake stroke is made possible by the fact that the force from the camshaft cam is transmitted to the rockers, tappet. The design of modern internal combustion engines means that the camshaft cam directly impacts the valve. The valve springs tightly press the valve back after the rocker runs off the tappet or the valve stem stops contacting the camshaft cam. There is a design clearance between the camshaft, cam, and the valve stem, valve end. This gap can be as small as 0.3 to 0.05 mm, is designed to compensate for thermal expansion of the inlet valve. The opening and closing of the intake valves at a well-defined moment is made possible by the angular position of the camshaft, which is exactly the same as that of the crankshaft. It turns out that the position of the camshaft at the moment of opening the intake valve strictly corresponds to the position of the crankshaft. Engine designs may differ, the number of camshafts may be different. The intake valve starts to open a little earlier than the moment when the piston is at TDC, top dead center. This means that at the very beginning of the intake stroke, when the piston starts to go down, the intake valve is already slightly open. This solution is called valve opening advance. Different powertrain models have different valve advance, and the range of variation is between 5 and 30 degrees. The intake valve closes with a slight delay. The valve closes at the moment when the piston in the cylinder is at the bottom dead center and then starts moving upwards. The cylinder continues to fill even after the piston has started its upward movement. This phenomenon occurs as a result of inertial movement in the intake manifold. The main faults that are directly related to the engine valves are valve bending, valve fouling and valve burnout. Valve bending is most often caused by a broken timing belt. No less often bends valves and at incorrectly exposed marks in the process of replacing the timing belt. Change the timing belt and align the marks on the pulleys of the camshaft and crankshaft need to pay extra attention. Failure of the valve mechanism is the formation of soot on the intake and exhaust valves, which manifests itself in increased noise during operation and a drop in power of the internal combustion engine, characterized by the appearance of metal knocking in the area of the valve cover on the cylinder head, and also problems with the valves are detected by flapping in the intake and exhaust manifold. Soot on the valves and seats does not allow the elements to fit tightly to each other, which leads to the loss of the necessary compression in the engine. Reduced compression means loss of engine power. Heavy soot also leads to overheating and valve burnout. Faulty valve springs can cause deformation of the cylinder head and sticking of the stem in the valve guide. Incorrect thermal clearance between lever and stem will cause severe valve knocking. In such a case, it is necessary to immediately engage in setting the manufacturer's required thermal clearance. Motorists call this procedure valve adjustment. Adjust the valves at certain intervals during the operation of the engine, and also if the specified opportunity to adjust the valves of the engine is initially provided by design. Inlet valve. The intake valve of the timing mechanism opens access to the fuel-air mixture into the cylinder and stops access before the start of the compression stroke. In the case of a diesel engine, the valve allows only air into the combustion chamber. When the timing belt breaks, the intake valves hang up because the camshaft stops turning. The valve plates, which are now open, strike the cylinder surface. The valves are positioned at an angle of 30 to 45 degrees from the vertical axis. The inlet valve plate is larger than the exhaust valve. The difference is due to the fact that when the inlet valve opens, a rarefaction is created in the combustion chamber, and when the exhaust valve opens, an increased pressure is created. The rarefaction force is lower than the pressure force, so the intake requires valves with a larger head area to allow the necessary volume of fuel-air mixture to pass through. Inlet valve design. A modern trend in timing design is to increase the number of intake valves per cylinder. This increases cylinder capacity and increases engine power. The intake valve has inner and outer cylindrical springs that are attached to the valve stem. The intake valve is actuated by a lever, rocker, from the camshaft cam, or, in most modern engines, directly by cam pressure. A spring ensures that the intake valve stem is in constant contact with the end of the rocker or cam. Principle of operation of the inlet valve. The timely opening and closing of the inlet valve ensures that the angular position of the camshaft is precisely synchronized with the same angular position of the crankshaft. That is, the angular position of one strictly corresponds to the specific angular position of the other. Depending on the engine model, there may be more than one intake valve per cylinder. To radically change the valve opening advance, a set of sport camshafts must be purchased before the piston reaches top dead center. The intake valve begins to open, that is, at the intake stroke, the valve is already ajar by the time the piston starts to move down. The valve opening advance is different for different engine models. The limits of variation are 5 to 30 degrees. Characteristic inlet valve failures. By far the most common valve failure is valve bending caused by a broken timing belt. The same thing can happen without a breakage if the belt was replaced by a non-professional who mistakenly set the marks on the crankshaft and camshaft, or camshafts, pulleys. Particularly dangerous breakage for modern complex engines equipped with variable phase timing and other high-tech systems. Another common failure of the valve train is overgrowth of the intake and exhaust valves with soot. As a rule, the problem can be detected at a fairly early stage by power loss and pops in the intake and exhaust pipes, metallic knocking in the cylinder head, and a drop in engine power. Deposition of carbon deposits on valve seats and valves prevents them from fitting tightly and reduces compression. As a consequence, engine power is also reduced. Spring failures can cause loose valve seating and lead to deformation of the cylinder head, sinking or sticking of the valve stem. A large thermal gap between the valve arm and the valve stem also results in a sharp metallic knocking sound and loss of engine power. Valve materials. The inlet and exhaust valves of automobile engines are disc-shaped. The valve is opened by a valve mechanism controlled by an eccentric cam. The operation of the cam is synchronized with the position of the piston and the rotation period of the crankshaft. For this reason, they are made of more resistant materials than inlet valves and are therefore more expensive. The valve guide sleeve is positioned coaxially with the valve seat so that a gas-tight contact is ensured between the valve working chamfer and the seat. The working chamfer of the valve and the seat are beveled at an angle of 30 degrees or 45 degrees. These are nominal chamfer angle values. Actual values may differ by 1 or 2 degrees from the nominal values. The valves and valve seats used in most engines have a nominal chamfer angle of 45 degrees. The valve is pressed against the seat by the action of a spring. The spring is held on the valve stem, some auto mechanics call it the valve stem, by the spring backing plate, which in turn is counteracted on the valve stem by a lock, knuckles. To dismantle the valve, it is necessary to compress the spring and remove the breadcrumbs. The spring and collar can then be removed and the valve removed from the head. Vehicle valve designs, auto valve heads, often referred to as valve plates by auto mechanics, can have different designs. They can be either rigid or elastic. A rigid head has high strength, retains its shape and has high thermal conductivity. It is also characterized by higher wear resistance. An elastic head, on the other hand, is able to adapt to the shape of the seat. Therefore, an elastic valve seals the windows securely but overheats, and bending when seated in the seat as the valve adapts to its shape can cause it to break. In the construction of valves, a head is commonly used, with a small cap protruding above the face of the valve. Such a valve is quite light in weight, has high strength and heat transfer, and a slightly higher price. Elastic heads are more common for inlet valves and rigid heads for exhaust valves. Cold air entering hot exhaust valves immediately after engine shutdown can cause severe valve damage. In engines equipped with exhaust manifold heads and or straight-through mufflers, cold air has direct access to the exhaust valves. Abrupt cooling can cause warping and or cracking of the valve. These conditions are not uncommon in cold, windy weather when the wind blows cold outside air directly into the exhaust system. Counterflow silencers with long exhaust pipes and a catalytic exhaust gas neutralizer reduce the risk of such a situation occurring. Materials from which the valves are made. The alloys from which car exhaust valves are manufactured consist mainly of chromium, which provides high heat resistance, with minor additions of nickel, manganese, and nitrogen compounds. If special characteristics are required, the valve is heat treated. If a valve made of a homogeneous material cannot provide the required strength and heat resistance, it is welded from two different materials. After machining, it is impossible to distinguish where the valve parts are joined. Valve heads are made of special alloys with heat resistance, strength, corrosion resistance, lead oxide resistance and high hardness. The heads are welded to rods made of materials having high wear resistance. In valves designed to operate under particularly severe conditions, carbide materials such as stellite are directed to the working chamfer of the head and the top of the car intake valve stem. Stellite is an alloy of nickel, chromium, and tungsten and is a non-magnetic material. In applications where corrosion resistance needs to be improved, the valve is alitized. Alitizing the working chamfer reduces its wear when using unleaded gasoline. An aluminum oxide film is formed on the valve surface to prevent welding of the steel valve chamfer to the cast iron seat. The valve is pressed against the seat by the working chamfer, hermetically sealing the combustion chamber. The seat is usually formed as a structural element in the cast iron cylinder head casting. Such a seat is called an integral seat. The seats are usually induction hardened so that unleaded gasoline can be used. This ensures that seat wear is slowed down during engine operation. As the seat wears, the valve sits deeper and deeper into the seat, recessed. In cases where corrosion and wear resistance must be particularly high, plug-in seats are always used. In aluminum heads, the seats and valve guide sleeves are insert-only. It should be noted that in aluminum heads the operating temperature of the exhaust valve seats is 180 degrees Fahrenheit, 100 degrees Celsius lower than in cast iron heads. Insertion seats are used as a salvage measure when rebuilding badly damaged integral valve seats. Seat deformation is a major cause of premature valve failure. Valve seat deformation can be reversible, as a result of high temperature and pressure, or irreversible, as a result of internal mechanical stresses. Mechanical stress is a force acting on a body that tends to change its shape. In conclusion, understanding the differences between the inlet valve and the exhaust valve is crucial for grasping how an engine operates. The inlet valve is responsible for allowing the air-fuel mixture into the combustion chamber, while the exhaust valve plays a vital role in expelling the combustion gases after the power stroke. Each valve has its own specific timing and function, contributing to the overall efficiency and performance of the engine. By recognizing these distinctions, you can gain a deeper appreciation for the intricate mechanics that drive modern vehicles. Thank you for watching, and we hope this video has clarified the roles of these essential components.